Hello everyone, welcome to another session on the machine learning series. Today we'll basically discuss more on decision trees. Right. In the previous class, what we discussed was we basically discussed about decision trees, basically how decision trees are being built. Right. So different criterion for building decision trees, right? Different ways you could actually build decision trees, right? And we also got into sort of formula specific terms of say how each one of those, how do you calculate entropy, how do you calculate information gain, and all of that, right? We also looked at what are the disadvantages of decision trees, right? So even though decision trees have certain advantages, we also looked at what are the disadvantages of decision trees, right? Say one of the main performance, one of the main disadvantages of decision trees being, say in terms of your accuracy, right? In terms of how well your decision tree is performing in terms of accuracy, maybe in comparison to other standard approaches, it is on the lower side. It's accuracy, right? And also one of the problems, also one more problem being it has high variance, right? So again, one of the main problems with decision trees is this variance, right? So finally, at the outset, right, when you look at it, what you basically have is you basically have a model, right, which is performing well, which is performing decently, but it suffers from high variance. Right? Now, basically, the next step is people started thinking, say, how better can we improve the performance of decision trees? Right? So, one of the main things which people saw, right? So, whenever they combined multiple decision trees, what they basically saw was they could actually see a reduction in the variance. Right? So that is what we'll discuss in the next few sessions. So basically, there are different ways of combining decision trees, which basically result in one obvious effect is your variance gets reduced. Your variance gets reduced by a good amount. One additional effect is your model performance also increases. Right. So this topic basically is called as say ensembling, however you call it. Right. So basically, what is happening over here is you're basically combining multiple decision trees. Right. What does it lead to is one obvious thing is obviously it leads to a reduction in variance. The other thing which leads to is it also helps in increasing the performance of your model. Right. So right. So we'll just talk with different ways of combining decision trees, right? So the one obvious this thing is say you build multiple trees, right? So you build multiple decision trees, right? So after you build multiple decision trees, maybe you just literally combine them, right? So one thing with this is this is as good as taking average, right? So you just build multiple trees and literally sort of just combine them, right? What is happening is you're just taking average of your whatever decision trees you built, right? So in terms of effect wise, it actually does not give much of an effect, right? So from there basically what happened is people are looking at what other different approaches could be tried, right? So now one famous approach which we'll discuss in this particular session is something which is called as random forest. Okay, so random forest basically tries to build upon this only. So basically you combine multiple trees, but it does so in a manner where it has made few changes to the algorithm, right? So these changes are the ones which makes random forest so effective, right? Random forest is actually very effective at say picking out patterns in the data in term, and also it is also performance wise it's very good, and even in terms of say variance it also is on the lower side, right? So basically what random forest does is it basically tries to introduce randomness in the whole tree building process, right? So just to give you an example, right? Say suppose this is your original data set, right? So this is your original data set. See, whatever we are discussing over here, so on this data set you literally build multiple trees, right? So this is what we were discussing over here. Now basically what random forest basically tries to do is, so you'll be building multiple trees. Say you're building 5 trees. Basically what random forest tries to do is it obviously introduces randomness right from what sort of data is supplied to each one of these trees, right? Basically all of these trees, right, do not have the same data. Obviously the source data is the same, right? The source data is the same original data set, but it basically tries to introduce randomness in how the data set which is created, right? Data set for each one of these trees is created. That's one. And it also tries to introduce randomness in how the trees select features for building, right? For building its nodes, right? So why? So why do you need to introduce randomness at these two stages? Right? First stage is where in the data stage. Second stage is in the features, whatever features you can select. So basically, the main reason for introducing randomness is basically each tree sort of learns a specific pattern, picks out certain specific patterns only. Right. So that each tree, no tree is sort of same. Right. So basically, each tree is sort of different because it basically picks out separate patterns because data set is different and the way in which the trees are built is different. Right. So that is what sort of the idea, that is what sort of ideas the idea is of random forest. Right. You basically have your basic building blocks as trees instead of just directly combining multiple trees. And what does it do is it sort of introduce randomness in first how data is applied to trees. That's the first stage. And second stage, it also tries to introduce randomness in which how the trees build out its nodes. Right. So yeah, we'll get into detail in that, but this is what at a high level is what random forest basically is. Right? This is what at a high level what all of random forest is. Right. Okay, so coming back to say we'll come back to the first level where randomness is introduced. So how randomness is introduced over here is something which is called as through an approach, which is statistical approach. Right? It is called as uh, bootstrapping. Right? So basically, what is bootstrapping? Bootstrapping is nothing but say this is sampling with replacement. Sampling with replacement is nothing but your bootstrapping. Okay, so suppose again, just for representation purpose, your original data set is of say 1 2 3 4 5 6 7 8, right? So this, assume this is your original data set, and in this, say suppose you're basically generating three different data sets, right? So assume this is your data set 1, right, and this is your data set 2, right, and this is your data set 3. Now basically what will happen in data set 1 is you're just basically sampling your above you're just sort of sampling your above data set, right? So we, at least for explanation's sake, we just assume it's nothing but 1 to 9. Now say suppose you've chosen 4, 5, right? So assume this is your data set and you've chosen this. Now in the normal sense of way, right, in normal sampling scenario, what happens is that whatever elements you've chosen over here, you can't choose over here, right? But since this is bootstrapping is nothing but sampling with replacement, right? You can again choose the same elements again. Say I suppose I chose 2. I've repeated 2. Again, repeat, when I say repeat, it's sort of, since this is sampling with replacement, so whatever elements you take out, you can choose it in other data set or other iterations as well. Right? So that is what the whole idea of for your random forest is. So 2 4, say I was in this setting, I just picked out. Right, so I have 5 elements. So this gets done. Next is this. So maybe now you see I've repeated 2 and 4 and 5 and 6. Maybe I'll just stop repetition. Right, now in this, now basically what I do in the third data set is say just this is my third data set. This is how basically I create 3 different data sets through bootstrapping. Right, this is what I do bootstrapping. Bootstrapping in a very simple language, it's bootstrapping is sampling with replacement. Okay, so this is what bootstrapping is. So coming back to how random forest algorithm actually works, right? So the first step is uh, now we have got now we have basically generated your data sets to be fed into each one of those trees, right? Now basically the first step is you randomly select k features, right? You randomly select k features from total m features. So this is for initial building out the tree, right? So initially while building out the tree, you just randomly select k features. You do not select all the features for building out the trees. And when you just go back to your decision tree, right, what basically used to happen is you have 10 features, 10 columns, 10 features. All 10 features were basically considered for splitting, right? You basically looked at what is the what is the information gain for each one of these features, and the one with the highest information gain, that is where you basically did a split on, right? So that was happening. That was what was happening in decision trees. Now, basically, what limitation is put over here is you're just randomly selecting k features from total m features, right? So k is obviously lesser than m, right? Now, whatever k value is there, this is obviously lesser than m, right? So the default, right? So default numbers for k, which is proposed by sort of say the original random forest algorithm developers, where basically k is for a regression problem, k should be 1/3. Obviously, there's no rule that it should always be the same. And for classification problems, k should be 1 by square root of the total number of columns. Okay. So this is 1 by square root of total number of columns. So this is what this is. So this is the first step. Now say you've generated your data sets, right? So in this part you've generated your data sets. So in the next part, what you've done is you have so this is like in each one of these data sets. So in each one of this data set, basically what you've done is you've just randomly selected k features. So the next step is basically this is like a normal tree splitting process. So among these k features, right? Among these k features, what you basically do is you calculate the root node d, right? You just basically calculate a root node d, right? Next, again, you just split your random nodes. So again, so from here, it's the same. It's a normal decision tree building process only. Then after that, you keep on continuing, maybe depending on whatever stoppage condition you have. So one thing with random forest is you sort of create your normal trees. You do not sort of hinder your trees. So obviously there are certain hyperparameters. There are certain stoppage conditions which are basically hyperparameters, right? So certain conditions like say number of estimators, right? You can easily choose number of estimators, what is maximum number of features, what criterion you're choosing, what is the minimum samples of your leaf, what is your maximum depth. So obviously there are different knobs which you can use so as to control the tree building process. But say coming to algorithm wise, right, this is what basically is your algorithm. All right. So this is for each data set. So maybe basically at the end, what you might do is for combination. So you just literally aggregate. Maybe you just take the average or you take the majority, right? So this process basically is called as bagging. Bagging is basically a combination of your bootstrapping, right? Bootstrapping plus aggregation, right? So combination of bootstrapping plus aggregation is nothing but your bagging. This is what bagging is, right? So you create your data set with bootstrap. You create data sets through approach called bootstrap. Then after your data set is created, you basically use this approach to build your trees. In this, so these are different. So at least say from an sklearn point of view. So these are the different hyperparameters which are actually available. Okay, so something which is called as n estimators. Then you have max features. Then you have something which is called as criterion. Then you have minimum samples per leaf. Right. Then you have something which is called as max depth. So these are the different. These are different which you can think of. This are different hyperparameters, right? So coming back, maybe I think the difference between parameters and hyperparameters, I think, which we have already discussed previously, right? So model parameters are the ones which the model is picking up from the data. The model is learning from the data. Hyperparameters are the ones which the user sort of inputs, right? So these are the values which is not learned from your data. So in which the user is obviously need to input those values. Obviously, there are certain default values which any library developer would have kept certain default values, but the option to change it is always there. So say maybe we can just have a discussion on what are these hyperparameters, at least from a random forest sklearn perspective, right? So criterion is nothing but your it's basically whatever you saw in decision tree, right? Either you can use a Gini or entropy, right? Gini or entropy information can. So that is what your criterion is. It can be either Gini or entropy. It is basically telling you on what this thing to split on, right? What to basically calculate. So this is for building your decision trees. Okay. So we'll start with n estimator. So n estimators basically is, again, from the, I think you can easily understand, you can easily get this from the name itself, right? N is a number, estimator is a number of trees, because trees are the basic building blocks, right? So this is nothing but your number of trees, a number of trees that you need to build, right? Criterion is basically what the criteria you need to use to choose your to basically choose your nodes, right? So max depth is basically what is the number of levels a tree can grow, right? So so you have basically selected your root node, right? So assume you have basically got this is your root node. Then you do a bunch of splits over here. So this basically is your first level. Then again you do a bunch of splits over here. This is again a second level. And again you do a bunch of splits over here. You're getting it, right? So this is your first level, second level, third level, and so on. So max depth is basically you have a constraint on that as well. Do you need only 5 levels or do you need 6 levels? That is basically max depth. Then there's something which is called as minimum samples per split. So there are both of it. So one is your minimum samples per split. The minimum samples per split is, so you basically, when do you know to stop, right? So the number of so only if for that particular node, right? In that particular node only, maybe if you have 10 samples, only then split it, or basically just stop it as a leaf node, right? So that is what is your minimum samples per split will tell you. Right. So next is max features. So max features is basically a k value, whatever we were looking at over here, right? K value. So that is what is your max features. So obviously the default ones are k is equal to 1/3 for a regression problem, and k is 1 by square root for a classification problem. But yeah, so it is, you can definitely input these values as well. Right. Then you have other. Then you have other parameters as well. Then you have other parameters as well, but these are the main ones. Okay. Yeah. So this is it. So this is what is random forest. Yes. Right. So you know the approach for generating the approach for generating the data set. You know the approach for randomly selecting features and how to build them. Right. Yeah. This is it. So yeah, this is most of it is covered. I think one main topic which is left out is something which is called as out of bag error. Right. So what is the main idea? What is the main sort of idea behind out of bag error is? So whatever data set you create, right? Whatever data set you create using bootstrapping. So what is happening over there is, say you have one third of your data is actually repeating, right? Say basically this is your data set. In this data set, basically what you see is only 2/3 of them are unique. One third of it is repeating data, because right, this is sampling with replacement. So in the same data set only, you could have a row with 1 as well, you could have a row with 2 as well. There's no restriction on that, right? So what is happening over here is you actually see one third of a data set is repeating. So what is happening over here is the model is actually training only on 2/3 of your data, because 2/3 is unique. Now basically, now what is out of bag error is, say you have the original data set, right? So this is like your complete data set, right? This is your complete original data set. Now in that 2/3 is used for training. So the 1/3, right? The 1/3 which is actually not there in your training data set, right? So that actually is converted to your test set, sort of a test set, right? So this is your complete training data set, right? So this is your complete training data sets. On the complete training data sets, you through Bootstrap you generate different Bootstrap samples, Bootstrap data set. In that, when you say consider one data set, in that only in that one complete data set, only 2/3 of them, right? 2/3 of them is what is unique. 1/3 is what is sort of repetitive. Now, basically, what you can do is you can just when you compare them that training data set, what happens is that 1/3 and 1/3 which is sort of repeating, which is actually not there. Right? Repeating basically means it's not there. So you can, that is actually used as a test set, and this error is called out of bag error. So it is actually actually use it random forest. I've actually found out of bag error to be actually a very good measure of your model performance. Yeah, obviously you do have your test set, you do have your validation set, and all of that is there. But I've actually found out of bag error to be actually a very good measure, right? A very good measure of model performance. Okay, so this is what is the sort of concept behind the out of bag error. Okay. Okay, guys. Then thank you. We'll just meet again in the next session. Thank you.